We are looking at Module 3, Chapter 6. Chapter 6 covers normal probability distribution. The first question, what percentage of normally distributed data lie within two standard deviations, either side of the mean? I hope you remember the empirical rule, the concept that if you start from the mean and you go one standard deviation away, it covers 68% roughly. If you go two standard deviations away from the mean, it covers about 95%, and three standard deviations away will cover almost everything, 99.7%. Now, how do we come up with that? We can use the Z table, and it results in 95.44%. As we look at this normal distribution curve, here's mu, you go one standard deviation on each side, and this area is about 68%. More precisely, 68.26%, and you can look at the rest of the aspect. For a continuous random variable, the probability of a single value of x is always 0, because for a continuous random variable, we need an area to be covered. Remember, a single value doesn't cover any area. Remember, the area, total area under the curve corresponds to total probability of 1. Because of that, on each side, we have 0.5. If I were to write this for you, on each side, it covers area equal to 0.5. The parameters of normal distributions are mu and sigma, the mean and standard deviation. What are the values of those for SND, standard normal distribution? Mu is 0, sigma is 1, the same thing as the Z-score that we discussed and the Z table. Find the Z value for a standard normal distribution such that the area in the left tail is 0.05. So starting with the drawing helps. In the middle, you have 0, and then you go so many standard deviations away. Here's a normal curve, 0.05 on the left side. Now, let's look at the table. You have the Z-score on the left column, and then, for example, if you look at this one is negative 3.6, if you look at this one is negative 3.61, so on and so forth. Inside is the area. So you look for the area of 0.05. Notice 0.05 doesn't exist. However, these two numbers are the closest we can think of. So negative 1.6 for negative 1.65. It's in between, so negative 1.645 will do the job, just in between. We can use a TI calculator for a case like this, and it's just as good. Second, variables inverse norm, put the following entries. In this case, area to the left. Always you put the area to the left, mu and sigma, and enter. It gives you the answer. Of course, how many decimals? If in this case we go with the same number of decimals, we see negative 1.645, because this 8 changes this 4 to 5. Now we are looking at a similar situation such that the area in the right tail is 0.1. So we want to find the Z-score. In this case, the area to the right is 0.1. Now, the area to the right is 0.1. What is left on the left side is 1 minus 0.1, or 0.9. So 1 minus 0.1 is 0.9. We are looking at the area on the left for the sake of looking up the table. And with that being the case, when we read this 1.2, and then in this area, we are looking at 0.9, which doesn't exist. It's between these two values. So 1.28, 1.29, we go with a number in between. Again, if I were to draw this, I would say this area is 0.9. And why are we using that? Because we need the area to the left. So area to the left, if we go with technology, and the answer is 1.282 instead of 1.285, because technology has a better answer for us. And by the way, you may notice that this number is closer to 0.9 than this number. You can look up the table. It's easier to read it from a large table. Find the following probability. Probability of z larger than negative 0.82. Graphing is always helpful. So we want the area larger than negative 0.82. We can look up the area to the left of negative 0.82 and subtract from 1. Negative 0.82 gives us the area 0.2061, subtracted from 1. There you have it. A second method is using the fact that you're dealing with the symmetrical shape. If you read for positive z-score of 0.82, so from negative infinity to 0.82 in the following manner. So look up 0.82. This area is identical to that, and it may be easier to read it in one shot. Now, TI calculator will help you get to the same answer using second variable's normal CDF. So take a look. You go with normal CDF. What about the lower? As you notice, right here we have negative 0.82. What about the upper? This goes to infinity. If we are going to look at this one, this goes to infinity. As far as the z-score is concerned, remember, 3 standard deviations covers about 99.7% on both sides. Therefore, if a number is larger than 3, in fact, 3.5, the table gives us 0.9999 with 4 nines after the decimals. Number 1000, this is what I use, and that's good enough. It will give you the proper answer. You can even use 500 or 200. That should work, but I put 1000 to be on the safe side. On the other hand, if I need to start from negative infinity, I would put negative 1000. As you can see, here's the answer from the table. Here's the answer we got from the technology, 0.7938. If we continue, if we want to stop at 8, this 9 changes it to 9, and that's exactly what we got here. The z-value for mu, it's always 0. Why is that? Because z is defined as mu minus mu over sigma. So 0 corresponds to mu. If you have a normal distribution where mu and sigma are given, then this corresponds to mu. Usually the normal distribution is used as an approximation to binomial distribution when NP and NQ are large. How large is good enough? In some cases, 5. In many cases, must be larger than or equal to 10 to be on the safe side. 3 out of 8 drinkers acquire the habit by age 20 if 300 drinkers are randomly selected using normal approximation to the binomial distribution. Find the probability that exactly 100 acquire the habit by age 20. All right, the very first thing we want to write is the given, because you're dealing with an application. 300, that's N. 3 out of 8, that's P. So you can calculate the Q as 1 minus P. You have to calculate NP and NQ to make sure they are large. So Q is 1 minus P. NP and NQ are both large. By that, we mean we are looking for number 5 or 10. And now we can move on. So we are interested in calculating probability of X equals 100, BD short for binomial distribution. Now remember, binomial distribution is a discrete probability, and we are approximating it with normal distribution, which is a continuous one. Probability of a single value is 0, if you recall from the previous page, simply because it doesn't cover any area. Therefore, they add and subtract a number known as continually correction factor. Statisticians use 0.5. Let's add and subtract to create an interval. Now we want to go from the X. So we went from binomial distribution to normal distribution. Now from X, we want to go to Z. That means we want to go to standard normal distribution. We have to use the formula for Z. To do that, we have to calculate mu, which is NP, and sigma, which is square root of NPQ. So mu, in essence, was calculated here already. Sigma is square root of NPQ. Needless to say, you have these formulas in your formula sheet. So calculating the z-score, putting 99.5 instead of x, results in negative 1.5502. So again, x minus mu, 99.5 minus mu, which we found it to be 112.5, over sigma, which was found to be 8.3853, results in this number. We're going to do the same thing to number 100.5. So we're going to repeat that with the second number. And now SND, standard normal distribution, we put the z. And therefore, we can look up the table. Now, as far as the z-score is concerned, it's between negative 1.55 and negative 1.43. As far as normal distribution is concerned, these two numbers that you have at the endpoints for this rectangular strip of blue would be 99.5 and 100.5, which correspond to those values. Looking up the table, we get 0.0158. We have to subtract one value from the other. So when we are approximating by binomial distribution, we use those transformations. Now, let's look at calculated point of view. Normal CDF, lower minus 1.55 or minus 1.55 can be calculated accordingly, negative 1.4311. Those are more precise answers. Normal CDF, 0.015. This 7 changes to 8 because of the rounding. If we were to use binomial distribution, binomial PDF, n is 300, p 0.375, and x is 100. Notice the answer, 0.15, and we are going to do the rounding, so 7 changes to 8. They all give us the same answer. So if the approximation is done properly, normal CDF is a good approximation of a binomial distribution. Bear in mind, in the old days, they didn't have technology. That's why they use normal distribution as an approximation. We're going to continue with the same question. We're going to add parts B and C. In part B, at least 125 acquired the habit by age 20. Needless to say, age 20, number 20 is an important number. It's the age, but it doesn't enter the calculation. So at least means we want x to be larger than or equal to 125. Now with that 0.5 continually correction factor, you have to think whether you want to use 0.5 and add it or subtract it. Therefore, are we writing the same thing, x larger than 125.5 or x larger than 124.5? By the way, the equality makes a difference because you're dealing with a discrete value. In this case, whether you put the equality or not makes no difference because a single value gives you 0 probability. Now, when we look at this one, probability of x larger than 125, that means discretely you're looking for probability of x equals 125 plus probability of x equals 126 all the way to n, which is 300. So you need the endpoint, namely 125. Now, if I put 125.5 here, the very discrete value, the very first integer is 126, and I'm going to miss 125. So therefore, we have to use 124.5. We repeat the same thing. We go to the z-score using x minus mu over sigma. That means we are moving from binomial distribution to normal distribution and now to standard normal distribution. Graph from the table or technology, we get 0.0764. Part C, at most 165 means x is less than or equal to 165. We are going to do the same thing. This is the endpoint 165, and what it means, we want the probability of x equals 165 plus probability of x equals 164 all the way to 0. So from 165, including 165 to 0. We can say x is less than 165.5. We can say x is less than 164.5. In other words, we can add 0.5, we can subtract 0.5, and now we need to figure out which one is it that we need. Remember, if you go with this one, less than 165.5, the first number is 165, and that's what we need. But if you go with the second one, the first number less than 164.5, which is an integer, is 164, and we missed the endpoint, namely 165. Therefore, we're going to drop this, and we're going to go with 165.5. Now, normal distribution, we calculate the z-score, and we go to standard normal distribution. The number is way larger than number 3.5. So 6.3206 is somewhere here, way into the right side, and that basically gives us no area to the right. Everything is covered almost 100%. IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. What percentage of people has an IQ score above 120? What is the maximum IQ score for the bottom 30%? So first and foremost, as we read what is given, ND, normally distributed, mu, sigma. So the very first thing is treat this as a word problem, application problem, write the given so you understand what you're doing. In part A, we want the probability of X larger than 120. And that means we are going to calculate the z-score, X minus mu over sigma, to go to standard normal distribution. That's why the formulas are helpful. Also, we have written the value of mu and sigma. We can easily plug in, look up the table. Now, what we want is larger than 1.33 somewhere here. We want this area. Now, one of the reasons drawing helps you have an idea, roughly, of course, what your answer should be. So because they are asking for the percentage, we change this answer to 9.18%. Otherwise, you don't have to. What is the maximum IQ score for the bottom 30%? So bottom 30%, you have to come up with the area that is 0.3. Now you got to look up the table to find the z-score. Because we want the IQ score, the idea is from the area, go to the z, from the z, go to the x. Take a look at this formula. In essence, you can find z, then replace the x and mu, find x with the cross product. That's the concept. Looking up the table or technology will result in a number between the two. If you do the cross product here, take a look. X becomes mu plus z times sigma. So x is mu plus z, you find a number in between, times sigma of 15, and you do the math. So the maximum IQ score is about this number, 92, roughly 92.125. Now, of course, when you answer that, you want to put a lot of decimals unless they ask you to do the rounding. If we were to do this by calculator, we find the area using inverse norm. Area to the left, mu, sigma, and that will give us the answer in one shot. Now, it is important to justify your answer, not just using a calculator, but go through the process so your reader can see what you're doing, and then, of course, you can use a calculator. Justification is extremely important. In this case, we are dealing with a case which is normally distributed and a mean of 6.0, standard deviation of 1.0. Before even we move on, we can just write the given first and foremost. The given right from here, we have a normal distribution, or ND, with mu being 6.0 inches, more specifically with the units, and sigma is 1.0 inches. If a man is randomly selected, find the probability. So if a man, and that's really the key, find the probability that his head breadth is less than 6.2. That means we want this one again, just as before. This is a normal distribution. We're going to go to SND by finding the z-score using the formula z equals x minus mu over sigma. Now, probability of z less than this number, and 0.2 is somewhere here. So what we are looking at here, it's about 0.2 here roughly. This doesn't have to be perfect. So what it does, it tells me the area is a little bit larger than 0.5. And that's why if you're looking up a table, if you're using a calculator and the number is off, you can tell, you should have an idea what you're getting, a little bit larger than 0.5. Now, when we look at the second case, it's the same question with the following difference. A man, now we are dealing with 100 men, otherwise identical. What does it mean? Instead of X, we are going to look at their mean X bar, and this formula becomes X minus mu of X bar over sigma of X bar. That's the thing. Now, what I want to write for you, and I want to remind you, is that mu of X bar is equal to mu. Mu of X bar refers to the mean of all those means. Sigma of X bar is sigma over square root of n. And so what happens, because you're dividing by square root of n the denominator, in essence, you're multiplying this one by that. So square root of 100 is 10. If you multiply that one by it, you get to the answer. This is a complex fraction. The denominator itself has a fraction. And so what happens when you look at the area, we're going to go all the way to number 2, which means we're going to cover a larger area. Again, you have to show your work. You have to justify your steps if you were to use a calculator. Notice the lower is negative 1 e to the e99. That is a very small number. If it has it, fine. If it doesn't and you have to put the number, put negative 1,000. That's just as good. You calculate and it gives you 0.57925. 2 can be changed to 3, giving you the same answer. Over here, we are doing the same thing. We are changing the sigma and we get to this answer, 0.977. Again, the point being you can use a calculator, but you have to justify your work. After doing those word problems, these questions are basic. We're not going to waste too much time. So we are looking at mu equals 0, sigma equals 1. So the essence is the z-score. And looking up the table, we come up with the answer. Look at this area. We want the area to the right of this number. So this is basically the z-score because mu is 0, sigma is 1. We are basically repeating the same thing because the mean is 0 and standard deviation is 1. We want the area from negative 2.13 to 3.77 using the z-score again. Why is that? I want you to pay attention to this and this. This is the reason. So we are looking at the z-score, look it up, you're done. Assume that a randomly selected subject is given a bone density test. And it gives us the mean, which is 0, standard deviation, which is 1, which in essence, we are looking at the z-score again. Draw a graph and find P19. What is P19? The 19th percentile. This is the bone density score, separating the bottom 19% from the top 81%. So what does it mean? We want the area to the left to be 0.19. Area to the right is 0.81. So with that being the case, we want to find the z-score. If you use a technology, it gives you the answer and you're done. If you use a table, area to the left, when it's 0.1922 from the table gives you this number, negative 0.87. When it's 0.1894, it's negative 0.88, which means none of them is 0.19, but the number we are looking for is in between, so you can choose the number in between. Either one is fine. This one is a tad closer than this, so you can go with that or go in between using the table. By now, especially for a case like this, I highly recommend you use technology to be on the safe side. Find the area of the shaded region. Okay, what really is important if we want to make a change, it's that this is the X value, if you will. We are going to the Z value if we are looking up the table. So probability of X between the two numbers, calculating the Z-score using the fact that mu is 100 and sigma is 15. So from normal distribution, we are going to standard normal distribution. Looking up the table will give us this answer. By the way, we are subtracting 0.6554 from this number because if you look at the graph, it gives you the area to 2.133 and then the area to 0.4. That's why you are subtracting. The assets in billions of dollars of the 4 wealthiest people in some country is given as 33, 29, 16, 11. Assume the sample of size n equals 2 are randomly selected with replacement from this population of 4 values. Number one, this takes a long time if the numbers are more. Okay, this does get involved. That's why it's a very small size. After identifying the 16, 2 to the power of 4, we are choosing 2, and there are total of 4, 2 to the power of 4. So that I'm telling you how to calculate this in general if the numbers are different. Different possible samples and finding the mean of each sample, construct the table representing the sampling distribution of the sample mean. In the table, values of the sample mean that are the same have been combined. So what do we mean by that? The fact that we are doing it with replacement, it means start with the first number, 33 with itself, then 33 with 29, then 33 with 16, then 33 with 11 because we are choosing 11. Then we go to the next number, 29. Choose it with 33, then 29 with itself, then with 16, then with 11, and continue with that thoughts. That's the concept. It creates the following table. So what I want everybody to pay attention to is that each and every one of them, and there will be a total of 2 to the 4 or 16 possible outcomes, has a probability of 1 over 16. To find the mean, add this 2, divide by 2, add this 2, divide by 2, add this 2, divide by 2, all the way to the end. These are the choices we have, and this is the X bar for each case. And each case, the probability is 1 out of 16. Now, what I'd like you to look at is the following. When you put the numbers together, such as 33 and 33, there's only one way out of 16, so it's 1 out of 16. However, if you're putting 33 and 29, also you put 29 and 33, they result in the same X bar, which is 31. That's why you have 1 out of 16 here, 1 out of 16 here, and it's 2 out of 16. And again, I understand it's equal to 1 over 8, but I want to keep it as 2 over 16 to make this clear to everybody. Now, there was not enough space to put this under this, but if we did that, this second column, which is the probability, they add up to 1, and this whole thing is called the probability distribution. Compare the mean of the population to the mean of the sampling distribution of the sample mean. What does it mean? We have 1, 2, 3, 4 pieces, divide by 4. That's the value of mean. So the population contains 4 pieces. That's what we get. How do we calculate this? There are 2 ways to calculate it. Just add these numbers and divide by 16. When I say these numbers, 33, this one you really have to account for it 2 times, or summation of X bar P of X. Just multiply this column by this column, add them up. I hope you remember that when we calculated the discrete, the mean for the discrete value, or it's called expected value. They are identical. Do the sample means target the value of the population mean? In general, do sample means make good estimates of population means? Why or why not? The sample means target the value of the population mean. That is, the mean of the sample means the expected value of the sample mean is equal to the population mean. Mu of x bar equals mu, what I was explaining the other page, and the concept that comes from CLT, the central limit theorem. The population of current statistics students has ages with mean mu and standard deviation sigma. Samples of statistics students are randomly selected so that there are 44 students in each sample. For each sample, the mean age is computed. What does the CLT, central limit theorem, tell us about the distribution of those mean ages? So the general idea behind that, so quickly I will go over that. A sampling distribution of a sample means is a distribution obtained by using the means computed from random samples of a specific size taken from population. For example, for samples of size n larger than 30, the distribution of a sample means can be approximated reasonably well by normal distribution. The approximation becomes closer to a normal distribution as the sample size n becomes larger. What we did in the previous page was this concept with a very small size to make it manageable. What is the conclusion? The distribution of sample x bar will, as the sample size increase, approach a normal distribution. And in that case, the mean of the sample means, that means add them up, divide by the size of the sample means, mu of x bar equals mu. By size, I mean how many of those we have, not the sample size. The standard deviation, sigma of x bar is sigma over square root of n. And that's exactly what we've been discussing so far, and we've used that already. So in this example, 44, n is larger than 30. The sampling distribution of the mean ages can be approximated by a normal distribution with a mean mu of x bar equals mu, and sigma of x bar is sigma over square root of n. Because we have n, that means sigma over square root of 44. So I wanted to explain the details, not just answering this is mu of x bar equals mu and sigma of x bar is sigma over square root of 44. I wanted to go over this concept of a CLT for you. Here's another interesting example. A boat capsized and sank in a lake based on an assumption of a mean weight of 137 pounds. The boat was rated to carry 50 passengers. So the load limit was, in essence, 50 times 137, which is 6,850. After the boat sank, the assumed mean weight for similar boats was changed to 170 pounds. In other words, that was a wrong assumption and it was underestimated. Assume that a similar boat loaded with 50 passengers and assume that the weights of people are normally distributed. The mean is 174.1 pound and the standard deviation is 35.1. Find the probability that the boat is overloaded because the 50 passengers have a mean weight greater than 137 pounds. So as we read this question, let's put in the information. Obviously, it says normally distributed. We have n equals 50. Mu is 174.1. Sigma is 35.1. So the very first thing is to write the given. We want the probability of x bar larger than 137. We are going to get to the z. To do that, we use z equals x bar minus mu of x bar over sigma of x bar. And remember, this is the same as mu. This is sigma over square root of n. Calculation will give us negative 7.474. That means almost everything from the table. When we go beyond 3 standard deviations, it's a lot more than 99% 0.7%. So this is minus 7.474. So it's 100%. It's 1. You can use technology or the table, and it pretty much gives you the same answer, 1. Now, the boat was later rated to carry only 15 passengers, and the load limit was 2550. Find the probability that the boat is overloaded because the mean weight passenger is greater than 170. So what happens, again, it's a normal distribution, but n is changing to 15, mu 174.1, and sigma is 35.1. So it's the same as before, those pieces of information. However, this 170, we want the probability of X bar to be larger than 170. Now, we do the z-score. Z is larger than negative 0.4524, and we find the answer between the two. The technology gives us 0.6745. Do the new ratings appear to be safe when the boat is loaded with 15 passengers? Obviously not, simply because this is fairly high, 67.45%. The point being, we are looking at the concept known as a quality control, and things have to be checked on a normal basis, especially when it comes to human lives. At an airport, passengers arriving at the security checkpoint have waiting times that are uniformly distributed between 0 and 10 minutes. All of the different possible waiting times are equally likely. Find the probability that a randomly selected passenger has a waiting time of at least 7 minutes. First, let's discuss the concept known as uniform distribution. Uniform distribution is a continuous random variable, has a uniform distribution if its values are spread evenly over the range of possibilities. The graph of the uniform distribution therefore becomes a rectangular shape. Properties. The area under the curve always equal to 1 because it represents the probability. There is a correspondence between area and probability. So probabilities can be found by identifying the corresponding areas in the graph using this formula for the area. The area is the width times the length, or in this case, the way we draw it may be height times the width. So we use the density curve. The graph of any continuous probability distribution is called a density curve. And any density curve must satisfy the requirement that the total area under the curve must be 1, because the total area under any density curve is equal to 1, and there's a correspondence between that and the probability. Therefore, the total area under the curve is 1 for this example, and from 0 to 10, so the width is 10, the height must be the reciprocal of that, 1 over 10. Take a look at this one. If the total area is 1, and we're going to go from 0 to 10, which means we cover 10 as the width, then the height can be easily calculated because the area is fixed. The area is not changing. The area is always 1. So this must be the reciprocal of that. Whatever this number is, the reciprocal of that. So we have that, and now we want the probability of at least 7 minutes. X is larger than or equal to 7. So from 7 to 10, this is 3 times the height, and that gives us 0.3. That's how you do the calculation. This is the end of chapter 6.